G'day. In this video I want to tell you a little bit about the first laboratory exercise, introduce what you need to do, what you're going to have to submit for it, and demonstrate the operation of the board in the required exercises. What I want to talk about is what you need to do to complete this lab. I'm going to explain the lab requirements in a bit more detail and cover what parts you need to submit before finally providing some demonstrations of what the board looks like when it's running the exercises that you've been asked to do. So overall, in order to undertake this lab, you need to get a lab kit, obviously, from the admin office on level 1 of K17. You also need to review the week 1 familiarization exercises to have an understanding of how the software that you're going to be using, Vivado, the CAD tool, works, and how the flow that you need to follow to design and implement a solution on using Vivado. I would recommend that you read the entire exercise sheet for Lab 1 from beginning to end before you even do anything, just so that you have an idea of what you're going to be doing. And then start carrying out those lab exercises from the beginning through to part 5 at least, and part 6 is optional. So the lab is going to be running during weeks 2 and 3, so you can get help during those weeks in the lab hours set aside for COMP3222 and 9222 in the brass and strings labs. You don't have to go to the lab that you're enrolled in. You can go to another one if you wish, assuming there's space available. If there's no space, then the people that have signed up for that lab have priority. Finally, for this lab, you need to submit your solutions for parts 3, 4, and 5, and you'll need to do that by the Sunday of week 3. I'll explain that in more detail in the following slides. So for this particular lab, you need to do the first 2 parts yourself. There are 6 parts altogether that are described within the lab. You need to submit parts 3 to 5. We provide templates, template code and test benches for parts 3 through 5. So to give you a bit of a start, so you really only need to fill in small parts of the code for each one of these exercises. In particular, you're going to be doing part 3 and archiving that. In order to do part 4, you have to complete a design of a decoder that's going to decode a particular 2-bit input and display a character on the 7-segment display. And once you've made that design, then you can go ahead and implement the code, because then you'll know what the code needs to be, and you can test and archive that part. For part 5, you also need to do some preparatory work, because it's not initially clear how you're going to rotate the letters that you need to display around the 3 7-segment displays. So you need to do a little bit of thinking and provide your design for that, as well as implement, test, and archive that. Overall, we want you to practice good code style, which means, focusing on indentation, capitalizing reserved words, using the right type of VHDL statements. So in this particular lab, you're only to use simple assignment statements, no behavioral statements at all. All right, as for the submission, for this lab, you're going to be submitting project archives parts 3, 4, and 5. These are archives that you create from the code, and I'll show you how you do that. You also need to submit neat electronic copies of your preparation for parts 4 and 5. In this course, if we ask for you to submit your designs, your work won't be marked unless you submit those designs. Only once you've submitted the design will we look at your code. So just remember that. In this lab, you need to submit your designs for parts 4 and 5. After you've created the archives and you have JPEGs or PDFs of the preparatory work that you've done, you can zip all of those files together and submit just the one zip file through WebCMS and ultimately GIVE. And that submission is due just before midnight on the 9th of March, which is the Sunday at the end of week 3. So you have the opportunity to seek help during weeks 2 and 3 from the lab demonstrators to help you with this lab. Note, however, that the second lab exercises will start in week 3. So if you want to have 2 weeks to ask questions about lab 2, then you'll need to start asking questions in week 3 for that. All right, let's have a look at the demonstrations. The first demo, or the demo for part 1, is pretty straightforward. You're going to be doing this by yourself. I'm not actually going to show you anything other than the expected result, which is what it looks like on the board. In this part, you're required to connect the 16 switches to the 16 LEDs and thereby be able to control the lights. So let's have a look at what that looks like in the flesh. Okay, I've just attached the board to my Vivado machine, and I'm about to program it with the bitstream for the very first part of Lab 1. As you can see, that changes the appearance of the lights, etc. And we should now be able to see that the switches are all connected to the LEDs directly. I can individually switch LEDs off or on using the switches that are provided on the board. Okay. In part 2 of the lab, you're expected to design a 4-bit 2-to-1 multiplexer as depicted in this illustration here. The way the mux is meant to be connected to the board is to have the selector bit connected to the switch number 15, and then to have the X input, the 4-bit input X, connected to switches 0 through 3, and the Y input, the 4-bit Y input, connected to switches 4 through 7. The output M, the 4-bit output, should be displayed on the 4 LEDs 0 through 3. Let's have a look at what that looks like. Right, updating the board with the bitstream for part 2 of Lab 1 results in a change of the display of the output, primarily because now we have implemented a 4-bit wide 2-to-1 mux, which is controlled by switch 15, that's the select input, and we have the lower 4 switches providing the X input, and the next for the Y input here. So when the switch is low, then X input is active, and so we can see that as we manipulate those switches, we get a change in display, whereas any other switches don't have any impact on the output here. All right, so we'll set up a bit pattern 1010 on the X input and 0101 on the X input and 1010 on the Y input. And now we should be able to flip between those two inputs just by selecting either the Y input or the X input to be displayed on the bottommost 4 LEDs. In part 3, the first submissible part of the lab, you're expected to design a 2-bit wide 3:1 mux as depicted here. The select inputs S0 and S1 are to be connected to switches 14 and 15, whereas the inputs, the 2-bit wide inputs U, V and W are to be connected to switches 0 through 5, W to switches 0 and 1, V to switches 2 and 3, and U to switches 4 and 5. The output M, the 2-bit wide output M, is to be connected to LEDs 0 and 1. So let's have a look at that. Right, switching from the part 2 design to the part 3 design, when we program the board, observe a change in the LED display. For part 3, the requirement is to implement a 2-bit wide 3:1 mux, whereby we use the switches here to implement inputs U, V and W respectively. Let's set them to be 1, 1, 0, 1, 1, 0 and 1, 1 respectively. And the two uppermost switches up here, 14 and 15, are used to control what gets displayed on the two rightmost LEDs here. So for input 0, 0, we're displaying input U. For input 0, 1, we're displaying input V, so 1, 0. And for input 1, 0, we're displaying input W, which is both LEDs being lit up there. Obviously, we can manipulate that by just toggling these two switches, that output, whereas the other switches have no impact on what's being displayed. If we select the U input, then of course it will be these two switches here that control the LED output. And if we slide this up, we see the rightmost LED being lit up. Asserting the switch to the left of that will provide the LED to the left of that being lit up as well. For part 4, you're to design a 2 to 7-bit decoder as is displayed here. The two input bits are to be provided by switches 14 and 15, and respectively the switch settings are to choose one of the 4 characters that are displayed here, respectively D for 00, B for 01, 3 for 10 and blank for 11 on the least significant or rightmost 7-segment display. So when we set the switches to 00, we're supposed to illuminate D on the 7-segment display. That means illuminating segments 1, 2, 3, 4 and 6 and keeping segments 5 and 0 dark. Let's have a look at how that looks on the board. The part 4 design is very different. When we program the board with that, we see the 7-segment display displaying the letter D. And that is because the two rightmost switches, switches 14 and 15, are now being used to control what letter is displayed on the rightmost 7-segment display. When they're both 0, the letter D is to be displayed. When they're 0, 1, the letter B is to be displayed. And when they're 1, 0, the letter 3 or the number 3 is to be displayed. And in fact, if both switches are set to 1, then a blank should be displayed. Okay, so that allows us to utilize the 7-segment display. In part 5 of the lab, we take the design a little bit further. In this case, we use a mux as well to determine what is to be displayed on the 3 least significant or rightmost 7-segment displays. We use switches 14 and 15 to control which switch setting is to be presented to the 7-segment decoder that's associated with each of the 7-segment displays. So when the switches are set to 0, 0, then we should be displaying the pattern DB3 on the rightmost 7-segment displays. When the switch setting is set to 0, 1, we should rotate that display by 1 position to the left and thereby be showing B3D. And finally, if the switch setting is set to 1, 0, then 3dB should be displayed on the display. In fact, it's a little bit more general than this, or the display, the design should be a little bit more general than this. It's up to you as to what bit pattern you implement using the switches 0 through 5, which are going to determine what is displayed on those 3 7-segment displays. I'll explain this a little bit further in the video. Reprogramming the board with the Part 5 design yields a different display again. In this design, the least significant rightmost 6 switches determine what letters are displayed on the 3 rightmost 7-segment displays. When the switches are high, it's a blank. D is in the low position, so 0, 0. 0, 1 gives us a B, and 1, 0 gives us a 3 in the rightmost 7-segment display. So we're going to program the display with the word DB3. So that is setting this guy to 1 and this guy to 3. And then we can use the 2 leftmost switches, 14 and 15, to control the rotation of those letters. So this requires you to think about how we should connect the switches to the muxes in order to achieve that outcome. So when the select is set to 0, we have DB3 written out. When the select is 0, 1, we have B3D written out. And when the display, or when the select is set to 1, 0, we have 3dB written out. The lab doesn't specify what should be displayed when selects are both 1. In my design, they just display the same as if we had the select set to 1, 0. Of course, we can change whatever the word is. We could make it, I don't know, D3B. Or D3D, then obviously we can rotate those 3 letters around. So this is not hardwired, it's determined by what we've selected as the word that gets rotated around using the select switches. repro. Finally, I want to show you how to archive a project so that you can submit your work for marking. To archive a project is easy. Select from the File menu the project submenu from which Archive can be chosen. Set the archive name to whatever you would like it to be. In this case, I'm archiving Part 5 of Lab 1, and it's going to be stored in the Lab 1 subdirectory of my COMP3222 Labs folder. Make sure that you have deselected these three items. Do not include any configuration settings, run results, or IP cache results, because they don't add any meaningful information to the archive for marking purposes. Hit OK when you've configured the archive correctly. And then we can confirm that the archive was written away correctly in the Lab 1 folder. To archive a project. So I hope you have fun with Lab 1 and learn something along the way. Good luck.